Imagine we have a flow field or a fluid field. For example, like in this picture. This picture shows the streamlines of wind flow pattern on the Earth's surface. At each latron point on this picture, we can define a variable like the net energy per unit volume. Let us assume this quantity E subscript V, E of V, or energy per unit volume, can vary both in space and time, and it is defined for all points in the 3D space. So even in the vertical, not just latron, even in the vertical direction Z axis, it's defined. So let us assume rho is the density of the fluid and it is constant throughout the space and time. So this is usually assumed in Navier Stokes, the density is constant. And the capital U is the velocity vector, and this can vary in both space and time. From basic calculus, we know that the total time derivative of a variable can be expressed in terms of partial derivatives like this. This is for the ith component or the x-axis component of the velocity. We get similar expressions for other velocity components also, and this is how the total derivative of the pressure looks. So total derivative of dp by dt is partial derivative of dp by dt, and all this partial derivative of del p by del x into dx by dt, del p by del y into dy by dt, and so on. And this is valid for any of the variables in the field. So if you want to get a total derivative, it can be expressed in terms of all these partial derivatives. We can write the net energy per unit volume as the summation of kinetic energy, gravitational potential energy, the pressure, and a variable S, which we will define in the next slide. So this variable S is a scalar which encodes the stresses in some form. That is, the gradient of S is equal to the viscous forces in the Navier Stokes equation. This is the del square or the Laplacian operator operating on the velocity field, and mu is the viscosity coefficient, and this is considered a constant. The individual components of the gradient of S, the individual components of the gradient of S look like this. This is the x-axis component, and these are the y and z axis components. Then we consider the total time derivative of the energy equation. So this is the total time derivative of EV. The d square x by dt square and d square y by dt square and the d square z by dt square are the acceleration terms. The total derivative of p and s are expanded in terms of their partial derivatives. So along with the d square x by dt square term, we have the partial derivative of p and s with respect to x. Similarly, we have the partial derivatives with respect to y and the partial derivative with respect to z in these other square brackets. Outside of all these bracketed terms, we have the partial derivatives of p and s with respect to time, del p by del t and del s by del t. These are not excess terms or erroneous terms. In fact, they show that the Navier Stokes equation is incomplete, or it is an incomplete description of the flow field and the flow phenomena. That is, the movement of the fluid or the mass transfer of the fluid particles due to the applied pressure gradient or due to the stresses in between the fluid layers results in alteration of the pressure gradients and the stresses. That is, because of the movement of the particles, the pressure gradient changes and the stresses also change. But the Navier Stokes equation does not explain this. That is, the Navier Stokes equation explains one part. It explains the part where the movement of the fluid is due to the pressure gradient, but it does not explain what happens to the pressure gradient once the movement is initiated. That is, because of the movement, the pressure gradient reduces and the stresses reduce or increase or whatever. So the Navier Stokes does not have any mechanism to explain that. It doesn't have any components, any terms to explain this rate of change of pressure gradient itself because of the movement. So there is, say first there is pressure gradient, it results in the movement of the fluid. The movement of the fluid actually nullifies the pressure gradient. So and there will be a specific time scale associated with this, that is, given a pressure gradient, we let the flow happen. After some time, all the pressure gradients is nullified and the flow stops. So there is a definite time scale associated with it, and Navier Stokes does not have any mechanism to estimate the time scale. Therefore, it is not a complete description of the fluid flow phenomena. It is incomplete, while this energy based description is more complete. We can also see that inside this square brackets we already have the xyz components of the Navier Stokes equation. Inside this first bracket with dx by dt factor, we have the x component of the Navier Stokes equation, and here are the y component and the z component equations. If we assume the total time derivative at each point is equal to the local or partial time derivative of the pressure and stresses, like here, if dEV by dt is del P by del T minus del S by del T, then all these terms inside the square brackets become 0, because the whole equation becomes 0. So inside the square brackets all these terms become 0. So we get this equation. This is the x component of the Navier Stokes equation. Similarly, we get the y and z components. The z component here has an extra g term due to acceleration due to gravity. If we want, we can expand the acceleration terms using this, that is, dw by dt can be written as all the sum of all these partial terms, or dv by dt or du by dt can also be, if we want we can write, because usually Navier Stokes is in this expanded form. So anyways, this is how we derive the Navier Stokes equations using a Bernoulli like principle, Bernoulli like energy equation. It is normally assumed that Bernoulli principle represents a very narrow restricted form of Navier Stokes equation with extra conditions like incompressibility, inviscid and all those things. But here we find that the Bernoulli principle is a more generic or a more complete description of the flow phenomena than even the Navier Stokes equation, and that we can derive the full Navier Stokes equation from this Bernoulli like energy equation. And one of the advantages of this energy form is that perhaps it makes proving the $1,000,000 question about the Navier Stokes equation much easier. With a little more calculation and clarifying one or two more concepts, we shall show that in the future videos that if the initial and the boundary conditions are smooth and continuous without any singularities, then the flow also remains smooth and continuous forever. This energy method not only makes solving the flow problems easier and more efficient, but it also makes the description more complete. We shall discuss about those things in later videos, future videos.